Okay, now we make a second claim. That is that A has no least upper bound. So to prove this claim, first note that if there's a magic number or not in Q that is an upper bound for A, then first of all or not has to be greater than 0. To see this, we notice that 1 is in A. Why? Well, we need to check the property that defines the set. And 1 squared is less than 2, and 1 is in Q. So it satisfies both properties, so that means it is in A. And 1 is greater than 0. Therefore, if R0 is going to be an upper bound, it has to be greater than or equal to 1, which is greater than 0. Okay, so let's, once we get that out of the way, there are two possibilities for R0. One, R squared is less than 2, and 2, R0 squared is greater than 2. Why are there only two possibilities? Because R0 squared is actually equal to 2 has been ruled out already. This is just the proof that square root of 2 does not belong to Q. So if there's anything like the square root of 2, this does not belong to irrational numbers. If there is any such number, then it's not a rational number. Okay, so we have two possibilities. Now let's explore each one. If R0 squared is less than 2, then let 1 over n be a small number to be fixed later, where n is in n. N is in the natural numbers. So we fix n large enough so that 1 over n is small. Then r naught is less than r naught plus 1 over n. And what we'll check now is that if we choose n large enough, r naught plus 1 over n squared is going to be less than 2. This is 2 over n times r naught plus 1 over n squared. So this number can be smaller than 2. Remember that r naught squared is less than 2. Indeed. Let's start by noticing that 2 minus r naught squared is greater than 0 by assumption. And then this means that there is rational number p less than 2 minus r naught squared, and that is at the same time greater than 0. It suffices to take p equal to 2 minus r naught squared over 2. Try to convince yourselves that this is the case. And of course 2 being an integer, r naught being a rational number, tells you that p must be a rational number as well. So now that we have placed a rational number between 2 minus r naught squared and 0, what we want n in n such that 2n or not 1 over n squared is less than p. Or in other words, what is the same what is equivalent to or not plus 1 over n is less than p times n. Okay, but now the existence of such n follows from the Archimedean property, then we'll prove in a short while. And therefore, we've found a number. So to summarize, we found a number Q in Q, where Q is equal to or not defined as R naught plus 1 over n, such that R naught plus 1 over n squared is less than 2. This implies, of course, that R naught plus 1 over n is an A. Therefore, R naught is not even an upper bound in this case. There's an element inside A that is bigger than R naught, right? So R naught is not an upper bound, so much less the least upper bound. Okay, so R naught squared less than 2 is not really a possibility. So it only leaves us with 2. So this means 2 holds, or means that the only possibility is that R squared, R naught squared, is greater than 2. Okay, let's put that even better. So in conclusion, remember that R naught squared cannot be equal to 2 because R naught is assumed to be in Q. And that's the starting point of the analysis of the real analysis of this course. The fact that we need to enlarge our set of numbers, of rational numbers, to include the solution to such a simple equation as x squared is equal to 2. So R naught squared must be greater than 2. But then this is the case, then R naught is not the least upper bound. Remember that what we've shown, if we have an upper bound, then R naught an upper bound, say a number p that is an upper bound, then p squared must be greater than 2. Otherwise, we can proceed as in the ruling out of the first possibility and show that it's not, in fact, an upper bound. So any upper bound must satisfy, any upper bound p must satisfy the p squared must be greater than 2. But then, so if R naught squared is greater than 2, then R naught cannot be the least upper bound. In fact, so indeed, if we reason like before, we can find n in n large enough so that r naught minus r 1 over n squared is the same time greater than 2 and less than r naught squared. And how do we make this happen? Remember that r naught is greater than 0, otherwise it cannot be cannot be an upper bound. There are positive numbers that are in A, so you must beat at least those positive numbers, such as 1. And so what I want to show is that if 2 is less than r naught squared, large enough n in n, two is still less than r naught squared plus 1 over n squared minus 2 r naught over n squared, over n. This again is equivalent to the existence of n, number n in n, such that r naught squared minus 2 is greater than 2 r naught n minus 1 over n squared. But r naught squared minus 2 is then greater than p greater than 0 for some p in q. It's similarly to what we did before, so we don't need to do it again. If you have a positive rational number, then there's another rational number in between, 0 and that rational number, and so, but we know there there is an n in n such that 2 over 2 r naught over n is less than p. Again, this follows from the Archimedean property. In Q, for Q. And this implies this in turn implies that P is greater than that 2 r naught over n, which is greater than 2 r naught over n minus 1 over n squared. For that n, and this is what we wanted to show, that there is a number r naught minus 1 over n. So there's a number n such that r naught minus 1 over n is in between r is such that r naught minus 1 over n squared is in between 2 and r naught squared. Okay, but we have that r naught minus 1 over n is less than, so it's smaller than r naught. But however, or on the other hand, this 1 over n is an upper bound for a. Right, so again, so to see this, we proceed as before. We take one r in A, and then r squared is less than 2, which is less than r naught minus 1 over n squared. That implies that r squared minus r naught 1 over n squared is less than 0. R squared, or r minus r naught minus 1 over n times r plus r naught minus 1 over n is less than 0. And just like before, so as earlier, you can conclude that r is less than r naught minus 1 over n. So this implies that are not is not the least, and this is to be stressed. Here is not the least upper bound. It may be an upper bound. In fact, A has infinitely many upper bounds in Q, but none of them are least upper bounds. Okay, so Q doesn't have the least upper bound property that we would like to have, so that's why we are constructing the real numbers. Okay. So we'll continue with the construction. We'll go back to the construction of the real numbers in the next video.